All right. So I promised you some neurosymbolic learning. In the first section, we basically saw that we need this way of really transitioning across different types of, I would call them learners, but basically in the literature, those are solvers and learners to basically differentiate between the type of representations they act upon. What I want to talk about is really a particular instantiation of this paradigm of using both learners and solvers to actually tackle a very specific type of machine learning problems, which we call concept learning. I will go, exactly like Hector did, from the more general to actually the more specific. And the question you can ask yourself is, what does concept learning have to do with pest doctors? So keep that in your mind. We'll get to that in a second. So fundamentally, obviously, we use AI for everything. Hector talked about alpha proof, but another great success of AI really based on more vectorial representations is really also AlphaFold, where the fundamental idea is you're given a sequence really which represents a protein structure, and your job is to figure out how it's going to fold itself from a planar space into 3D space. And classical approaches so far achieved a global distance test score, which really measures nothing else than how far you actually are from being in the right epsilon space of what should be the case in reality. So you know how the protein folds, you have your solution, and you measure the distances between where your solution places the molecules or the atoms and really where the atoms should be. Where there was a jump using deep learning from 60% to 92.4%. And the position error really moved from 2.83 Armstrong, which is 10 to minus 10 meters, to 0.96. So really by using deep learning, there have been incredible improvements carried out in the performance of AI models. But using the same paradigm, we can do very interesting things in the wild. So every human I know sees the first three signs that says, well, that's a stop shield. Well, if you train a deep learning model, something like YOLO, and you add the right wrong pixels at the right spot, YOLO will say the first three signs are, please, maximal speed of 45 kilometers an hour. And it will drive through those signs. If you look at the fourth one, which basically says, well, you know what, you really do have to go right here, well, YOLO will say that's a stop sign if you put the right wrong artifact within that particular image. So whilst those systems learn really well, they basically have the problem that we actually don't know or cannot really explain why they learn so well. That's basically what happened here as well. So if you think about having your Tesla Cybertruck driving in auto mode, you might want to rethink that simply because it's never seen a light pillar of this type. It simply didn't consider that to be a light pillar. I mean, just when that's a normal street I can plow through, which obviously physically led to a bit of a crash. And it's even more interesting, you can intentionally actually trigger this behavior. This is a super interesting experiment in a paper by Kaspersky, where they basically looked at what do I actually need to do to hack such a system. And it turns out that if you have the right pixels at the right place, those are those funny little glasses here, you can actually get a classifier, an image classifier, for example, to say that this person is exactly the same as this person. Well, I think it's pretty obvious to all of us that that's not the case. So whilst we have carried out extreme jumps in the performance of AI models, especially with the deep learning paradigm, and that's what I'm mostly going to be concerned with, we still have the problem that these deep, what we call sub-symbolic models, so deep models which look at the world as being a distribution of vectors and actually learn on these distributions, are not really trustworthy. And that has to do with the fact that we actually do not really understand how they work. They don't really even try to be explainable because of the number of parameters. So if you use something like ChatGPT, you're probably looking at hundreds of billions of parameters which you are interacting with. Try to explain that to a single human brain. That's not going to happen. There are some hidden biases, but that's not really what we're going to be interested in. And they often also hallucinate. So often they just generate output which really does not make sense of the input that was given in. So that's basically the one side, right? That's the sub-symbolic side. It's fast, it learns quickly, but it basically makes errors and cannot really explain why. We have on the other side the symbolic learning side. And as already pointed out, we have major challenges there pertaining to scalability. So the particular type of symbolic learning I'll be interested in this talk is concept learning. Let's look at what that is. So imagine that you're given this particular graph, which we will call a knowledge graph. I'll not get into the formal definition thereof. And you were told that in this graph, the node Louvre and Tour Eiffel are positive examples for a particular class of things, whilst the nodes Lily and James are negative examples for that particular class of things. What would you say would be a description of Louvre and Tour Eiffel, which describes those two nodes, without describing Lily and James based on this data? I told you there would be questions. Yes. Any suggestions? See, that's not what the data says, though, but it says something very close to that. Things located in Paris, exactly. So that would be a description according to this graph, which would describe these two entities. So Louvre is located in Paris, the same holds for Tour Eiffel, and that does not hold, according to this data, for Lily and James. And that's exactly what we would actually want our AI models to do. We want to be able to give them data. We want them to be able to give us answers in a language we understand, but also answers that are reliable. Concept learning, so far the classical view on concept learning, does exactly that, but doesn't do that particularly fast. There's obviously the obligatory technical slides for the more technically inclined people, because we want to be technically clean here. So formally, concept learning is a form of supervised machine learning with the caveat that we use background knowledge. So background knowledge basically meaning that we have a formal representation of the world in which we operate. That formal representation is in some formal logic for the aficionados. Commonly, I'm going to be looking at ALC. We assume that we're giving some positive and negative example. And what we really want to do is learn a model, which we are going to call a hypothesis. And our hypothesis should be such that for all the positive examples, our hypothesis holds. So if you remember the graph we had before, we had Louvre and Tour Eiffel as example. They are both located in Paris. Our hypothesis was things located in Paris. So our hypothesis holds for our positive examples. And it should also be the case that the hypothesis does not hold for negative examples. So Lily and James were not located in Paris. Problem solved. But we can look at this problem in a slightly different way by basically defining a continuous function, which we're going to call the Q function, the quality function. And that Q function is really going to tell us how good our solution is. And what we really want to find is a hypothesis which maximizes that Q function over the space of all possible concepts, right? As you can see, there is already there a way to transition between this more discrete view of things and actually a view which is more of reinforcement learning. And we'll get into how to do that in a second. So why does this not scale? Really quickly. Fundamentally, the way this is commonly solved is we start with some training data. The training data comes from some background knowledge or a knowledge base. We generate a first candidate solution, and then we iterate upon this solution using a refinement operator. And that refinement operator, which I'll show an example in a second, does nothing else than creating further hypotheses. We then call a quality function, and that quality function demands reasoning. As mentioned before, reasoning is expensive. In the worst case, we're looking at things that are NP-complete or even undecidable, depending on the language that you are dealing with. So, but once we've called that retrieval function, it basically tells us which candidates are good, and we iterate further until we basically get to a solution, or we run out of time, of memory, of money, and then we stop. Fundamentally, that's how things go. So for the example we had before, we would start, for example, with the most generic concept, which says, well, everything is good. So that's basically our first hypothesis. We look at Louvre and Tour Eiffel. Yep, belongs to the state of things that exist, great, but so do Lily and James, so that's obviously a pretty bad solution. We'll then call an operator, which will generate further possible hypotheses. We'll score the hypothesis and refine that further until we get to where we actually want to find things that are located in Paris. Okay, as I said, each of these steps is expensive, And it turns out we spend roughly 90% of our time actually doing the reasoning part. So to fix this problem, actually be able to do this type of explainable machine learning, we actually need to rethink how we represent the problem. That's fundamentally where these neurosymbolic aspects come into play. And there are three major challenges, really. It is that actually retrieval, ergo finding the set of instances of one of these concepts, is super expensive. That's where, as I said, we spend roughly 90% of our time. Number two, the quality functions that we've used so far are myopic, short-sighted. What that really means, I'll show you technically in a second. And generating candidates is also super expensive. So how do we solve those problems? Can we actually exploit, if you think about the more deep learning view on things, so the sub-symbolic representations, those are really fast actually. They're not good, they don't really know what they're doing in the sense of a formal representation, but they're really fast at finding solutions. So can we find algorithms that exploit the best of both worlds? That's fundamentally one of the many things that we are interested in. I want to take you now to the trick. So how we actually solve this problem. And solving this problem has something to do with 1666. So who knows what was happening in Europe in 1666? Has something to do with the first image. The bubonic plague. That's what was happening between 1665 and 1667. We had the plague. Well, that doesn't sound too great, does it? But actually for science, it was great because it turned out that researchers went like, I'm not staying in a big city. I'm going to go into a little place and they do my research there. That's what Isaac Newton did. And he moved to this place, which is called Woolsthorpe Manor. And Woolsthorpe Manor, does anybody know what this tree is? I mean, you should actually recognize the type of tree. Apple. An apple tree, exactly. So Newton's gravitational equation and so on, it is told that this is exactly the tree under which he was sleeping when the apple fell on his head. Obviously, that cannot be true because there's no 300-year-old apple tree, but it's good to get tourists around. So it is the tree, and you should go there and have a look at it. What's more important is when Newton moved back to Woolsthorpe Manor, his parents' house, he basically started thinking about questions as simple as, how do I compute pi? We know that pi is a transcendent number, so basically it's infinite and so on. But how do we compute a good approximation? So up to that point, computing pi was done this way, using regular polygons. And you would basically say, well, I have an inscribing regular polygon and I have an inscribed regular polygon. I am going to take really basically having a unit side or diagonal. I'm going to take those two numbers, average them, the surface of the inscribing and inscribed regular polygon, and say, well, this is my approximation of pi. So if you do that with squares, it's actually pretty clear that you get the inscribed square having a surface of 2, the inscribing square having a surface of 4. That gives you an approximation of pi, which is exactly 3. To get to the first 50 numbers of pi, you need something along the lines of 2 to the 38 sides for your polygons to actually get the first 50 numbers right. That's a computation that takes you roughly 3 years. Remember, there were no computers back then. You had to do that by hand. And in his so-called Annus Mirabilis in 1666, Newton actually simply changed the way he represented the problem to actually have a significantly faster representation. I'm not going to get into the technical details. That's not that important. By the way, the fundamental idea is you can look at the problem in a fully different way by thinking of circles as being functions. That's one. By knowing that you have basically Pascal's triangle, which gives you the binomial formula. That's 2. And number 3, by remembering that actually you can compute pi via integrals. So by using these 3 components, you actually find an infinite series, which is an exact expression of pi. And instead of needing 3 years to compute the first 50 numbers, you actually need 3 days. So a reduction of runtime just by looking at the problem differently. And that's fundamentally what we do. We change basically the way we look at the problem. And by changing the way we look at the problem, we can actually solve the problems of finding the right instances and the like significantly more efficiently. I'm not going to delve into all of technical details. You're going to see a bunch of images But I do want to give you some idea of how we tackle this problem from a neurosymbolic perspective. So our hypothesis, which I'll plow through really quickly, is that because ML operates on formal representations of the data at hand, and that because ML assumes a suitable formalization of the learning task itself, it might be that by changing representations or problem formalizations, we might get more appropriate, more efficient ways really of solving exactly the same problem. And that's really what we look into. So the idea behind a lot of our work, and that's really an emerging discipline in machine learning, is learning with multiple representations to leverage several representations side by side to improve machine learning processes. How do we do that in our case? Problem number one, retrieval. What is retrieval all about? I tell you things located in Paris. I give you background knowledge, and it's your job to give me the list of things which are located in Paris. So if you think about the graph we had before, it will basically be going through all the node and asking, do you fulfill all the conditions to be located in Paris? Yes, no. And as I said, that inference requires classically an exponential amount of time, exponential the size of the number of nodes. That's really fundamentally what an algorithm would have. A classical algorithm like the Tableau algorithm would have to build to actually answer that question. It will go through all of the possibilities. So all of the possibilities which come from the domain knowledge. So if something is located in Paris, for example, you might have a subsumption hierarchy, so a hierarchy of relations, which says to be located in, you can also be simply placed in. So placed in would be a sub-relation, a relation of lower order than located in, and the algorithm would say, are you located in? Potentially not in the data, but in the data there is that you are placed in. So actually by logical inference, you must be also located in. We build such trees. The exact details are not important. Important is they take a lot of space in memory. They take a lot of time to build. Can we actually fix that by switching representation? And the representation switch, which is currently being looked into and which we actually started looking into around 2020, is actually rethinking the way we represent graphs. So if you think about graphs, the graph that I showed you, for example, that is nothing else than a tensor, actually a generalization of a matrix. So by changing the way we look at graphs and saying a graph is a tensor, this operation of retrieval is actually nothing else than picking ones and zeros in a tensor. That we know how to do fast. So we actually have NVIDIA chips and the like for exactly that purpose. So we can actually show that retrieval is exactly equivalent to running queries against a tensor under obviously certain conditions. This basically, for the aficionados, this tells you exactly why this one-to-one mapping actually exists, provably exists, under the assumption that we are looking at the closed world and a fully materialized knowledge graph. So the magic now is how do we move from this graph representations actually to tensor representation? If we can do that, we can actually solve the retrieval problem really quickly. Well, the fundamental idea is if we think about these assertions like Louvre is represented in Paris, we can index all of the information, all of the nodes in our graph, give them numbers. The same goes for the relation between things. We can also assign numbers to those. And suddenly we're describing where should I have a 1 and where should I have a 0 in a three-dimensional tensor. 1 if the indexes for the subject, the predicate, and the object, so for the three terms in my assertion, are found in my list of assertions, and 0 in all other cases. I get a very, very sparse tensor. Don't worry too much about the technical details here. But then what we can now show is that the fundamental elements of querying actually map to an operation we know from math, which is called slicing. So simply by looking, by rotating and chopping parts and bits of my tensor, I can actually directly start answering questions. For those who know their way around databases, I have my atomic operations. I need joins, right? I need ways to be able to take these atomic operations on my graph and actually join them together to create more complex queries. Well, it turns out we can steal from physics and actually map this operation of joins to what is known as an Einstein summation. An Einstein summation does nothing else than actually giving us an operator that can take several slices, in this case, and merge them to yet another slice. So basically, for an example, this query, which basically does nothing else than finding all of the Fs, which are such that there is a particular E1, a particular node, which is connected to these Fs. These Fs know another U, and that U is a unicorn. That would be an example of the type of queries which will come out of our data. Well, we can actually map this to 4 operations, 3 slicing operations, and 1 Einstein summation. Details are not important. What is really important is that we can do this fast, whilst we cannot do that fast when we're looking at reasoning. Ergo, equivalent problem represented a totally different way leads to a significantly faster solution. We've benchmarked that, and basically what this shows is that if you do this well and you represent these tensors well, it's not only that you solve the problem of retrieval faster, you actually solve in general the problem of querying faster. So classical mechanisms for storing graphs use really relational representations, which we know from relational databases. Well, it turns out that we can not only gather, ergo read the data faster, what we can also do is query the data faster. What these plots show is really nothing else than the so-called queries per second. You can focus on that. And these colored bits basically show different variations of our algorithms compared against classical algorithms on a log scale. And you basically get an order of magnitude faster just by looking at the problem in a different way. All right. And if you map that to exactly the problem at hand, which is a problem of concept learning, actually you get even greater gains. You get actually 2 orders of magnitude faster. Important bit, so major outcome here, just by changing the way I look at the problem, exactly like Newton did in 1666, I can actually take the retrieval question, map it to tensor operations, which is actually pretty wild because a priori they don't have much to do with each other, and actually solve the problem way faster. So good. We can, however, rethink the problem in a totally different way, and that's what I'm going to leave you with. Let me see, how much time do I have? Still have a little bit of time. We can look at the problem in a totally different way, and that is basically directly connected to Hector's talk. We can actually think of the problem of finding the right quality function as a reinforcement learning problem. So the type of algorithms you'd use to solve problems like playing chess, you can actually use exactly in this setting as well. The assumption here is that we have embedding functions. Embedding functions do nothing else than taking a graph and mapping that graph actually to a vector space. That gets really technical. I'm not going to delve into that. There's a whole theory around Clifford algebras, which I'll be happy to talk about if you're interested, but we're not going to do that. Just assume that those things exist. Then you can actually do the following. Classical functions, so classical quality functions are handcrafted and look roughly like this. Details are not important. What's really important is their behavior. They basically want to do actually 3 things. Number 1, they want to ensure that a concept is good if it retrieves positive examples. It's bad if it retrieves negative examples. And we also want to have short concepts because actually we want to take those concepts and transform them into natural language which is understood by humans. The assumption is the shorter the better. That's really all these equations do. But if we think about it, if you think about a refinement tree, what they really do is they look at a node in the tree where we started with the top concept and refined it further, and basically only ask the question, how good are you? They don't ask the question, how likely are you to produce actually a solution to my problem? But think about the same problem from the perspective of chess, right? You have a chess position in front of you. How do you know whether that position is any good? Number 1, it's already a checkmate for you. Yay, I'm done. My score is 1, I can move on, I've beaten my opponent. Number 2, I have a sequence of move which is likely to lead to checkmate, right? So actually it's the future gains which are actually important for my position, right? The position is good if it will lead me in the future to checkmate. Translated to concept learning, a position is good if it will lead me to a hypothesis which fulfills my criteria in the future. So existing quality measures do not do that. And I will just give you some insights into how we can map concept learning actually to reinforcement learning, assuming that we have a vectorial representation. Well, it turns out to build a reinforcement learning problem, I need a few components. I need a concept of state. So I need to be able to describe which state I'm in. Well, that will be my concept in the refinement tree that I have. I need a reward. So I'm in a particular state. I assume I have an agent. The agent carries out an action, and the environment basically tells me in the next step how good that action was and gives me a reward. Well, I can also model that rather easily by saying you get a reward of 0 if you've not found a solution, and you get a reward of 1 if you found a solution. And what I also need to have is really a definition of actions. So which actions can I take when I'm in a particular state? Well, I told you that as well already. That is exactly that operator which generates the next children to the state in which I am. So actually, concept learning is the same as reinforcement learning, assuming that I have a Q function which basically tells me how good, or that I can learn basically a policy. And I can learn such a policy because if I have a vectorial representation, well, although I have an infinite number of states, because I have an infinite number of concepts, I can map this back to actually a deep learning problem by saying, I am going to start with a quasi-random neural network. I am going to train my model by looking at problems to which I have the solution. And because I have a vectorial representation, I can take my states, create vectors out of them, and shove them into a neural network to actually train a quality function. And it turns out it works rather well. Importantly, existing operators are complete in the sense of they are guaranteed to find a solution if a solution exists. But what we can show is that we can do that significantly faster, an order of magnitude faster, and the expressions which we generate for human legibility are also an order of magnitude shorter. So we solved the quality function problem. At least there's the first solution. Again, there is a switch share representation. The switch is I look at the problem from a different perspective and I ask, isn't this a reinforcement learning problem? Can I use my standard techniques for that? Candidate generation, I'm not going to delve into in too much detail apart from one thing. We can actually, once we have these vectors, obviously all hell breaks loose because we can rethink the problem in a totally different way and say, what if I simply say this is a machine translation problem? I have one language, which is my positive and negative examples. I have another language, which is the world of concepts, and I only need to learn a machine translation algorithm between the two. Turns out we can do that. That we call concept synthesis, where we basically take our positive and negative examples, generate vectors out of them, and simply take a deep neural network, which we then train to actually spit out expressions in the formal language we're interested in. Main advantage being that so the output of the neural network, we can actually check formally to check, does it really fulfill the criteria which we had for our positive and negative examples? And it turns out it works not only really well, especially when you have complex data, it turns out that it also works really fast. So we basically can now solve problems in 0.08 seconds. Let me see, do I have times here? Yes. In 0.08 seconds, assuming that we have the right neural architecture, where other algorithms actually need up to 230 seconds. So have we solved the problem? Of course, I'll show you the shiny part. Turns out that, well, exactly like you have limitations of LLMs that hallucinate, as soon as you do a little bit of change or you spot the right positive or negative examples to shove into this, you basically get catastrophic results. But still, what was important to me, and that basically already brings me to my summary, is the following. Turns out that ideas from 1666 actually make sense. Switching representation is an old trick, but it works really well, especially in the domain of machine learning. And it allows us now to bridge between this symbolic representation and this sub-symbolic representation, now actually create neurosymbolic algorithms that perform well on the one side, but also have results which we can check as humans on the other side. So improvement in runtimes as well as in F measure, but the major question that I did not talk about and that remains open is how can we find the right representation at the right time? So far I've told you which representation to use and I've told you how to use it. And to me it seems to be the major question really in AI. how do I actually represent well to solve my problem? I do not have an answer to that question, but if you have one, please let me know. I'll be happy to discuss it with you. Thank you very much.